Picture the very beginning of our universe. Imagine the Big Bang. It's an unimaginable explosion of energy and light. The universe is born. It expands rapidly, cooling as it goes. This is the dawn of our cosmos. But this early universe wasn't the dazzling spectacle we might imagine. Instead, it was shrouded in darkness. This is a time we call the cosmic dark ages. These dark ages lasted for hundreds of millions of years. The universe was a very different place back then. It was much smaller and hotter. It was filled with a dense fog of hydrogen gas. This gas acted like a cosmic curtain. It blocked light from traveling freely. We can't see this era directly with our telescopes, but we can use our understanding of physics to piece together this cosmic puzzle. Studying the Dark Ages is crucial. It's like looking back at the universe's baby pictures. We can learn about the conditions that led to the formation of stars and galaxies. We can understand how the universe evolved from a simple state to the complex one we see today. The Dark Ages hold the secrets to our cosmic origins. In the aftermath of the Big Bang, the universe was a chaotic soup. Energy and matter swirled together in a hot, dense mix. As the universe expanded and cooled, protons and electrons, the building blocks of atoms, combined. This formed the simplest element, hydrogen. Hydrogen is abundant. It's the most common element in the universe. This hydrogen, however, was not the kind we find in stars today. The early universe was filled with neutral hydrogen. This means that the hydrogen atoms had an equal number of protons and electrons. They carried no net electrical charge. This seemingly insignificant detail had a profound effect on the universe. Neutral hydrogen is a very effective absorber of light. Specifically, it absorbs ultraviolet, UV light, the same type of light that gives us sunburns. As the universe cooled and more neutral hydrogen formed, it began to act like a dense fog. This fog prevented light from traveling freely. The universe became opaque, shrouded in darkness. The universe couldn't stay dark forever. Something incredible began to happen within the dense fog of neutral hydrogen. Gravity, the architect of the cosmos, started to pull matter together. Huge clouds of hydrogen gas collapsed under their own weight. These collapsing clouds became hotter and denser, eventually reaching temperatures and pressures high enough to ignite nuclear fusion. And so the first stars were born. These early stars were not like the stars we see today. They were much larger, hotter and more massive. They burned brightly but lived short lives, ending in spectacular supernova explosions. These first stars were the universe's first light show after the Big Bang. The birth of these stellar giants marked a turning point in the history of the universe. Not only did they pierce the cosmic darkness with their brilliant light, but they also profoundly changed the very fabric of the cosmos. The first stars were the key to ending the cosmic dark ages. The intense ultraviolet radiation from the first stars and galaxies streamed out into the surrounding space. This UV light had enough energy to knock the electrons off of the neutral hydrogen atoms, a process called ionization. As more and more hydrogen atoms were ionized, the universe began to change dramatically. The fog of neutral hydrogen that had shrouded the universe began to clear. Light could now travel freely across vast distances. The universe was becoming transparent. This period of transformation is known as the epoch of reionization. It was a cosmic renaissance, a time when the universe was bathed in the light of the first stars. Reionization didn't happen overnight. It was a gradual process that unfolded over hundreds of millions of years. As more and more stars and galaxies formed, they created ever-increasing amounts of ionizing radiation. Slowly but surely, they pushed back the darkness, transforming the universe from opaque to transparent. Section 5. Echoes of Creation. The cosmic dark ages are long gone. The universe today is awash in light from billions of galaxies. But the echoes of this ancient era still resonate throughout the cosmos. They are imprinted in the faint afterglow of the Big Bang, known as the cosmic microwave background radiation. This radiation, discovered in the 1960s, is a treasure trove of information about the early universe. Scientists study the cosmic microwave background to learn about the conditions that existed during the Dark Ages. They look for subtle variations in the temperature and polarization of this radiation. These variations can tell us about the distribution of matter in the early universe and the processes that led to the formation of the first stars and galaxies. By studying these echoes of creation, we can piece together the story of how the universe evolved from a simple state to the complex one we see today. It's like being cosmic detectives using faint clues from the past to solve the mysteries of the universe's origins. Section 6. The Hubble's Legacy. For decades, the Hubble Space Telescope has been our eye in the sky. It has revolutionized our understanding of the universe, peering deep into the cosmos and revealing a tapestry of galaxies stretching back billions of years. Hubble has shown us that the universe is teeming with galaxies of all shapes and sizes. It has allowed us to witness the awe-inspiring beauty and vastness of the cosmos. However, even Hubble's powerful gaze has limits. Its vision is most clear when observing visible light. The most distant objects in the universe, those that existed during the Dark Ages, have their light stretched by the expansion of the universe. This stretching shifts the light into the infrared part of the electromagnetic spectrum. While Hubble can observe some infrared light, it's not ideal for studying the faintest and most distant objects. To truly unlock the secrets of the Dark Ages, we need a new, even more powerful telescope. We need a telescope that can see the universe in a different light. Section 7. A new era of exploration. Enter the James Webb Space Telescope, JWST. Launched in late 2021, JWST is the most powerful space telescope ever built. It's designed to observe the universe in infrared light with unprecedented sensitivity and resolution. This makes it the perfect instrument for studying the faintest objects in the cosmos, those that existed during the Dark Ages. JWST is equipped with a suite of cutting-edge instruments that allow it to study the universe in ways that were previously impossible. Its primary mirror, made up of 18 hexagonal segments, collects light over an area more than 6 times larger than Hubble's. This allows JWST to see fainter objects and resolve finer details. JWST's ability to observe in infrared light is crucial for studying the Dark Ages. Infrared light can penetrate the dust and gas that obscure our view of the early universe. It allows us to see the first stars and galaxies as they emerge from the darkness. With JWST, we are entering a new era of exploration. The telescope is already revolutionizing our understanding of the early universe. It has captured stunning images of the most distant galaxies ever seen, providing us with glimpses of the universe as it was just a few 100 million years after the Big Bang. JWST's observations are helping us to answer some of the most fundamental questions about the universe. How did the first stars and galaxies form? How did reionization unfold? What was the nature of the early universe? These are just a few of the mysteries that JWST is helping us to unravel. The data from JWST is transforming our understanding of the universe's evolution. It's providing us with a more complete and detailed picture of the cosmos than ever before. We are on the cusp of major discoveries that will rewrite our understanding of the universe's origins. The story of reionization is a testament to the power of light. It shows us how light can transform the universe, clearing the fog of the Dark Ages and illuminating the cosmos. Light is not just something that allows us to see, it's a fundamental force of nature that shapes the universe we live in. Today, billions of years after the epoch of reionization, the universe is filled with light from countless stars and galaxies. This light carries information about the objects that emitted it, their composition, temperature, and motion. By studying this light, we can learn about the universe's history, its present state, and its ultimate fate. The study of light has been instrumental in our understanding of the universe. From the discovery of the expansion of the universe to the detection of gravitational waves, light has been our guide, revealing the secrets of the cosmos. The universe is not static. It's constantly evolving, changing and expanding. The epoch of reionization was a pivotal chapter in the universe's story, but it's just one chapter in a much larger narrative. The universe continues to evolve today, driven by the forces of gravity, dark matter and dark energy. New stars are born, old stars die, and galaxies collide and merge. The universe is a dynamic and ever-changing place. By studying the universe in all its complexity, we can gain a deeper appreciation for our place within it. The more we learn about the universe, the more we realize how much more there is to discover. Each new observation, each new discovery raises new questions and pushes the boundaries of our understanding. As we continue to explore the universe and unravel its mysteries, it's important to reflect on our own place within this vast and ancient cosmos. We are a product of the universe, born from the same stardust that makes up the stars and galaxies. The story of the universe is our story. By understanding our cosmic origins, we gain a deeper understanding of ourselves and our place in the grand scheme of things. The universe is a vast and awe-inspiring place, full of wonder, beauty and mystery. As we continue to explore it, we are sure to make new discoveries that will amaze and inspire us. The cosmos is calling, and we must continue to explore.